Electric Field, Part 1. Good morning. Today we're going to explain a new chapter that is the electric field. In the first paragraph of this chapter, we're going to explain the concept of the field, any field. Here we have Earth. This is a body S. Earth attracts all objects that is found at its vicinity by a force F that is called the gravitational force. The formula of this force depends on the mass m and the mass of the body s. It is given by this expression F equals gmm over d squared. M is the mass of Earth and m is the mass of the object. D is the distance between the center of Earth and the center of the object. G is a universal constant. It's equal to 6.67 times 10 exponent minus 11 in the SI. Note that returning back to this formula, we notice that this force depends on the mass of the body. This law, in general, shows that the force of gravitation depends on the mass of the body. That is to say, any object at a certain distance is attracted by Earth. The more massive the body is, the greater the magnitude of the force becomes. Then, the mass of the body, of this body, the Earth and body, are responsible for the force of interaction between them. As a result, their masses are responsible for the force of attraction F. On the other hand, the force of attraction F, we know that the force of attraction F represents the force of a terrestrial attraction or the weight of the body S. What is the formula of the weight of the body? The force represents the weight of S at a point A, F equals to W, which is equal to m times g, where g is the gravitational field at this altitude. Hence, we obtain F equals to m times g, which is the force of gravitation. The gravitational force is proportional to the gravitational field. The constant of proportionality is the mass m, which is a positive constant. And as a result, the force F, the force vector F, and the gravitational field vector are parallel and have the same direction. So we want to draw it. Here is the gravitational field vector. This is G. The direction of these two vectors have the same direction and they are parallel because the constant of proportionality is the mass, which is a positive constant. So we write that as magnitude, F equals to m times G. If we want to compare the two formulas of F, because they are equal, we write mg equals to g m times m over d squared. We can simplify by m, and we get that the magnitude of the gravitational field becomes gm over d squared, which is at a point A. The magnitude of the gravitational field vector at the point A is equal to g times m over d squared. M is the mass of the Earth. D is the distance between the center of the Earth and the center of the object at a certain height, A, where the force of gravitation acts. The mass of the Earth is responsible for the gravitational field. The Earth attracts all objects, or it creates at its vicinity a field that is called the gravitational field. The value of this gravitational field at a certain point in its vicinity is given by the expression. Note that the quantity responsible for the presence or the emergence of this field is the mass of Earth. The magnitude of the gravitational field depends on the height or the distance from the center of Earth. Now, note that all forces at a distance are a result of a field. In this case, it is a gravitational field. Let's take another example. A magnet, for example, attracts, for example, a metallic ball by a force F. This force is a force acting at a distance created by the magnet. This is the source of the force F, which is the magnetic force. Then the magnet creates in its vicinity a certain field that we call the magnetic field. The magnet creates in its vicinity a magnetic field we denote it as B vector, where F and the magnetic field are proportional as this formula. This is the gravitational force. This is the gravitational field vector. The force and the gravitational field vector, or the force of terrestrial attraction and the gravitational field created by Earth, are proportional. The constant of proportionality is the mass of the solid S that is found at a certain distance from the center of the Earth. Here, the constant of proportionality concerns the body that is subjected to the magnetic force. Then the magnet creates in its vicinity a magnetic field, B, where the force F and the magnetic field B are proportional. This constant can be positive or negative. If this constant is positive, F and B have the same direction. On the other manner, they have opposite directions. If, for example, here we have a point charge, a positive point charge, let's call it Q. If we place at a distance from this charge another one, small q, this charge will exert on the other one an electric force. If q is negative, then uppercase q will attract lowercase q by a force F. The charge q creates a force F on the smaller charge q, which is a force acting from a distance. Then the charge q creates in its vicinity an electric field, which is denoted as E. Hence, F and E are proportional. F equals to a constant multiplied by E. This constant concerns this charge. To determine this constant, we have to do the following. The charge Q creates in its vicinity an electric field E. Earth creates in its vicinity a gravitational field G. When we place here a certain mass, this mass is therefore subjected to a force F that is equal to m times G. When we place a charge here in the electric field of Q, this charge is subjected to a force F equals to Q times E. Note that let's place any charge, for example a neutral one. There will be no interaction between the two charges. For example, let's place here a particle of wood. This is a particle of wood. The overall charge of this one is equal to 0. Hence, the force acting on it, the electric force acting on it becomes 0. Then all bodies that is placed in the vicinity of this charge is under the electric field of this charge. But if its charge is equal to 0, we don't obtain any force. Now, in this paragraph, we're going to talk about the electric field created by a punctual charge. Here we have a region where we have an electric field E. Here's another region where we have another electric field E in a different direction. When placing in this field a point charge Q1, which is positive, then it is subjected to an electric force F1, which is equal to Q1 multiplied by E, as in the previous paragraph. Note that F1 and E are proportional vectors. As a result, F1 and E are parallel and have the same direction because Q1 is positive. Then, if you want to represent the electric force to which Q1 is subjected to when it is placed in the electric field E, we draw it in this direction, parallel and having the same direction as E. This is F1. Now in the other example, when placing in the electric field E a point charge Q2 which is positive, then this charge Q2 is subjected to electric force F2 which is equal to Q2 multiplied by E. If placing another point charge Q3, then Q3 is subjected to an electric force F3 which is equal to Q3 multiplied by E. Now, if you want to draw F2, F2 and E are parallel vectors and they have the same direction because Q2 is positive, then F2 and E have the same direction. Then we draw F2 in this direction. In the third case, F3 and E are proportional, so they are parallel, but Q3 is negative, then F3 and E are opposite vectors. So we draw F3 like this, opposite to E. All point charges that are found in an electric field are subjected to an electric force F equals to Q times E. Q is the charge on which this electric field acts. This force has the same direction as E if the charge that is found in the field is positive, and the force becomes opposite to the field when the sign of the charge is negative.